The continued saga of gas laws. So this is where we left off. So to summarize, this is Boyle's, all of these gas laws. And the problem is, which one do I use in which situation? So Boyle's law, pressure times volume is a constant. Charles' law, volume over temperature is a constant. Gay-Lussac, pressure over temperature is a constant. Avogadro's law. But this is good if the number of moles and the temperature is constant. Charles' law, if the pressure and the number of moles is constant. So how do I remember which one, right? But if you think about it, wouldn't it be nice if there was just one equation, maybe one equation to do everything with? Well, if you look at this, every time we see pressure, right, here and in Gay-Lussac, it's in the numerator. Every time we see volume, it's also in the numerator, all three times. The two times we see temperature, it's in the denominator, and number of moles is in the denominator. So what if we combined them? One equation to rule them all. So you see PV over NT could be a constant. This constant is called R, because I invented it. It's called Rob's constant. No, just kidding. Right? This is called the ideal gas law. We frequently write it this way, PV equals nRT. R is referred to as the universal gas constant. You need to memorize this. It's 0.08206 liters, atmospheres per mole Kelvin. So that's the value of R. You may see different numbers in different applications. They would have different units to go with it. All right. So we're going to do a bunch of problem solving. I'm going to show you how you can use this. So the ideal gas law, this is kind of interesting. The ideal gas law, what's very nice about the ideal gas law is if I can measure pressure, volume, number of moles, and temperature, if I measure three of these, I can get the fourth one because R is a constant. So for example, if I measure the temperature, pressure, and number of moles, I can get the volume. Or if I want the pressure, I can measure the volume, the number of moles, and temperature, and so on. What's really cool is if I measure the pressure, volume, and temperature, I can get to moles. And remember, the whole idea of the mole concept is that I can get from moles, I can get to particles, which I can't determine experimentally, and it's all about making easy measurements. Measuring pressure, volume, and temperature are pretty easy to measure. We'll do problems with this a little bit later on. Now going back to expressing it this way, all right, another way to look at it. This is R. That means under one set of conditions it's going to be R, which means under a second set of conditions, this will always be true. And by the way, how do we know it's 0.082? The last experiment, experiment 12, we're going to come up with that value. Anyway, if P1V1 over N1T1 equals R, and that equals P2V2 over N2, then we can set these equal to each other. And now we have, anytime you have two sets of conditions, you can use the ideal gas law in this way. So let me go through a couple of examples. All right. One little detail. This comes up, the textbook makes a huge big deal about this, and it's not that big a deal, all right, but it is important that you know STP stands for standard temperature and pressure. Standard temperature is 273.15 Kelvin, or 0 Celsius. Standard pressure is 1 atmosphere. So all this means is if we tell you that if we say a gas at STP, I've told you the temperature and pressure. But you do need to know STP means 1 atmosphere and 273 Kelvin. Right? It's not as big a deal as the textbook makes it out to be. All right. So if we solve problems using the ideal gas law, what's very interesting is if anything that's the same on both sides. So for example, it can cancel, right? If N1 is the same as N2, it'll cancel. So watch this. If the pressure and temperature are constant, if we back up, right? Charles' law, constant temperature and number of moles, excuse me. This slide's wrong, isn't it? Actually, so this should say pressure and number of moles. I'll fix the slides. Pressure and number of moles are pressure and temperature are constant, my bad. Pressure and temperature are constant. See how these cancel? This is Avogadro's law. My mistake here, this is Avogadro's law, not Charles' law. Okay, we'll fix that later. So we'll fix it later. That's Avogadro's law, not Charles' law. Right? But if volume and number of moles are constant, that's Gay-Lussac's law. If pressure and number of moles are constant, that's Charles' law. So it doesn't really matter what you call the law. It matters that you can work with it. So for example, a gas at STP occupies 25 liters. What is its volume if it's brought to 1.65 atmospheres and 10 degrees C? So let me just go through this problem. So what we do is we make a list, right? A gas at STP, so the pressure is 1 atmosphere, temperature is 273 Kelvin, and we're told it's 25 liters. It's brought to 1.65 atmospheres, 10 degrees C, which is 283 Kelvin. We want to find the volume. Now, you notice nothing is said about the number of moles in here. So we have no choice but to assume that the number of moles is not changing. So we'll call number of moles in 1, 1, but that means N2 is N1. So if we take this equation, and in this case the number of moles are constant, so now we have a new equation. The textbook calls this the combined gas law. Again, I don't really care what you call it. So now, just to do the algebra, so cancel out, if you start here, cancel out things that are the same on both sides, right? Now we rearrange, we want to solve for V2, so we multiply each side by T2 and divide each side by P2. So P1 V1 times T2, T1 times P2. Again, you can review the algebra, and then we're going to plug the numbers in. 1 atmosphere, 25 liters, 383, right? And we get 15.7 liters. Very important to do this step problem solving wise because it's really easy to plug the right number in the wrong place. Right? All right. So bottom line is, if there's 2 sets of variables, you can use it this way. 2 temps, 2 volumes. Now let's go back to this one, PV equals nRT. Okay? If there's only 1 set of variables. So for example, let's just do a problem. What's the pressure of 0.205 moles of nitrogen at 20 degrees if it occupies 5 liters? So there's my pressure, right? We don't know. We're trying to find the pressure, but we're told the volume is 5. We're told the number of moles is 0.205. And we're told the temperature is 20, which is 293. Take this equation, PV is nRT. We're trying to solve for P, nRT over V. And then we plug and chug, 0.205 moles. R, remember R from a few slides back, that's the value of R. Okay? That's the units. And then 293 for the temperature divided by the volume. All right, so I'm going to let you walk through these. This is a good, when we've done this step before, go ahead and click through it. Hit pause on the video so you can try it on your own. Right? So how many moles of helium in a 12-liter container at STP? So again, there's only 1 set of variables here. So we're going to put the pressure is 1 atmosphere. The volume is 12. We're trying to find the number of moles. It's at STP, so the temperature is 273. So I'm going to, you can hit pause. All right, so there's the equation. So now we're going to rearrange the equation to solve for N, PV over RT. And now we're going to plug in the numbers, P, V, R, T. And then we just do the math, and it's going to come out 0.535 moles. Okay? So what this shows is you now have 4 ways to get to moles. So we've had using mass and molar mass to get to moles. We've done a huge amount of this. Using particles and Avogadro's number to get to moles. Back on the material, the last set of slides actually before this, we used molarity and volume to get to moles. And now you can use PV over RT if it's a gas. How do you know if it's a gas? If there's pressure and temperature, it's a gas. I guarantee you on the final, I'm going to ask a question. I'm going to give you 4 or 5 things and say get to moles. And I'm going to give you the mass. I'm going to give you a molarity and a volume. I'm going to give you a number of particles. If you can't get to moles at the end of this class, something went wrong in the class. All right, try this one. So what mass of hydrogen gas is contained in a 4-liter balloon at 745 millimeters of mercury and 30 degrees C? So that's about the mass. Now you're told it's a gas, but if you weren't told, you're given a temperature and a pressure. So let's play with the gas law. P, right? We can't use it here. We have to have it in atmospheres because R is in atmospheres. So this is the conversion. 4 liters. We don't know N. 303, that's 30 plus 273. How are we going to get the mass? Right, so hit pause. Okay, back from pause. How do you get the mass? Well, we can get mass from moles, right? Going back a slide, whoops, here. we can get mass from moles. So we have to get moles. So how do we get moles? Well, we have the ideal gas law. And we can plug in the numbers, and we can get the number of moles. But the question wasn't the number of moles, the question was the mass of hydrogen. So we take the moles. Hydrogen is H2, so it would be 0.32 grams. Okay, now, of course, if we can get moles, we can get to moles of something else. That means gas stoichiometry. I know you guys are thrilled about this. All right, again, I told you when we first did stoichiometry, all stoichiometry is the same. All right, it's one way or another you're going to get to moles of something using one of those 4 methods of getting to moles. Then you're going to use the balanced chemical equation to get to moles of something else. And then you're going to get out of moles using one of the 4 ways. All right, so what I think we're going to do here, because of the time, is I'm going to go through and do 2 of these, but I'm going to go to the 3rd video so that we can go through them and not make the videos too long. But you can try this one on your own, and then you'll have to go to video 3 to get it solved. Whoops.